Good day to all. Myself Dr. Vibha, Department of Electronics and Instrumentation Engineering, working in SRM Institute of Science and Technology, KTR campus. Today we are going to see about electrical measurements in Unit 1 under the subject title Electrical and Electronics Measurements and Instrumentation. Introduction to this subject. Electrical and electronics measurements and instrumentation is a core area in electrical engineering focused on the principles, techniques and devices used to accurately measure electrical quantities like voltage, current, resistance, power and frequency. It is crucial for the design, testing and maintenance of electrical and electronic systems encompassing the both classical and modern measurements method. The core concepts are measurement systems, units and standard, instrument classification, measurement error, calibration, sensors and transducers. So, first, what is analog and digital instruments? Analog instruments produces analog signals, whereas digital instruments produces digital signals. Analog signal is continuously varying signal and take infinite values for a given range. In digital signals, it is discrete time signals which are generated by digital modulation. Examples for analog instruments is ammeter and voltmeters. Digital instruments examples are resistors and transistor. Analog signals are denoted by sine waves, whereas digital signals are denoted by square waves. Analog instruments memory is stored in the form of wave signals, and digital instruments memory is stored in the form of binary digits. Analog instruments draws large powers, whereas digital instruments draws less power. Moving parts are present in analog instruments, whereas there are no moving parts present in the digital instruments. Analog instruments are not flexible and has a less accuracy, whereas in digital instruments it is flexible and has higher accuracy. Classification of analog instruments. The analog instruments are classified according to the quantity they measure. Example, current, ammeter is used. For voltage, voltmeter is used. Electrical instruments are classified according to the type of current that can be measured. Direct current or alternating current, or it can be both direct and alternating. Analog instruments are also classified as indicating instruments, which indicates the magnitude of the quantity being measured, recording instruments, whereas it gives a continuous record for the quantity being measured, and integrating instruments, which gives the summation of which the product of time and electrical quantity, and direct measurings, which converts the energy of measurand directly into the energy that actuates the instruments, and comparisons, the instruments measures the unknown quantity by comparing with the standard measures. Classification of electrical measuring instruments, it can be absolute or secondary. Under the secondary instruments, it is further classified as analog and digital instruments. Analog instruments can be of deflecting type or null deflecting type instruments. In deflecting type instruments, it is classified as indicating instruments, recording instruments and integrating instruments. Absolute instruments. The instruments gives the value of the electrical quantity to measure in terms of constant and its deflection. This instrument is known as absolute instrument. It is also called as primary instrument or indirect instrument. These instruments are not required to compare with the standard values. Example, tangent galvanometer. Secondary instruments. This instrument gives the value of the quantity to be measured directly into the deflection. Instrument is called as a secondary instruments. It is also called as a direct instruments. Example, ammeter, voltmeter, wattmeter, etc., which are the examples comes under the secondary types of instruments. Classification according to the nature of the operation. Instruments can also be classified based on the nature of the operation. They majorly falls into the secondary type of instruments, which is divided into four major parts: indicating, recording, integrating and null deflection instruments. Indicating, it displays only the value of quantities per time of measurement. Example, ammeter, voltmeter, wattmeters, examples of the indicating instruments. Recording instruments, it displays and records the reading of the electrical quantity at per time of the measurements. Example, ECG and X-rays. Integrating instruments displays the record and add the numerical value of the reading of the electrical quantities. Example, energy meter and ampere hour meter are the examples. Null deflection instrument shows the reading of the electrical quantities without the deflection angle at per time of the measurement. Example, potentiometer. Classification according to the electrical supply. So, based on AC and DC, it is classified as AC instruments and DC instrument. So, AC instruments connected to the AC supply. Further, it can also be classified into single phase AC and three phase AC. Example, moving instruments, induction instrument, electrostatic instrument, dynamometer instruments and electrostatic instruments are the examples of AC instruments. DC instruments converted, it connects with the DC supply. Example, PMMC is the best example of the DC instruments. Classification according to the effects. During the various magnetic effects, electromagnetic induction effects, electrostatic effects and thermal effects, chemical effects, etc. are the more chances to get the applications or the system to get damaged. So, multiple types of instruments are used to measure and compare the unknown quantities with the standard values. These instruments protect the devices. So, the classifications are moving coil, moving ion, induction instruments, electrostatic, electrolytic and hot wire instruments. Galvanometer. A galvanometer is an instrument used for detecting the presence of small currents or voltage in a circuit for measuring their magnitude. It is used for measuring feeble current accurately. It is also known as electric current detector. So, it is D'Arsonval galvanometer. It is a moving coil type galvanometer. It works on the principle that when a current carrying coil is placed in a magnetic field, it experiences a torque. This torque which is produced will be proportional to the current passing through the galvanometer. So, the picture shows the moving coil type of the instruments. So, the torque equation will be obtained from the equation NIAB into sin theta, where theta is a 90-degree field of the coil which is called as radial field, and for a radial field torque will be NLAB, restoring torque, which is called as a K theta, where K is the restoring torque per unit twist, also called as a torsional constant. So, when you are equating both the equation, NIAB will be equal to K theta, where I is equal to K theta by NAB. So, which can be written as I is equal to G theta. G is nothing but galvanometer constants, which is equal to K upon NAB, which will be proportional to the theta. Permanent magnet moving coil instrument, which is also called as a PMMC instrument. It is most accurate type of DC measurements. So, the construction, the working principle of this instrument is same as the D'Arsonval galvanometer, and the difference being that a direct reading instrument is provided with the pointer and the scale. So, the picture is shown here. So, for this the torque equation will be first finding the deflecting torque TD, which is NBI DI, which is equal to GI, where G is equal to NBI D. The spring controlled torques provides a restoring torque, TC is equal to K theta. So, equating the deflecting torque, which is equal to spring torque, TC is equal to TD. Upon equating both the torque, we can find the theta value will be G upon K into I. So, I is proportional to K by G into theta. Electrodynamometer type instruments. The electrodynamic instruments are capable of services as a transfer instruments. Their principles uses as ammeter and voltmeter in laboratory and measurement work is for the transfer calibration of working instruments, and a standard for calibration of other instrument as their accuracy is very high. These instruments are used as AC voltmeter and ammeter, both in the range of power frequency and lower part of the audio frequency range. The construction is, it has a fixed coil, moving coil, control and moving system. First, fixed coil. Magnetic field is produced by a fixed coil which is divided into two sections to give more uniform field near the center and to allow the passage of instrument shaft. Moving coil is wounded either as a self-sustaining coil or else a non-magnetic former. Both the fixed and moving coils are air-cooled. Controlling system. The controlling torque is provided by the two control spring. This spring acts as a lead to then the moving coil. Moving system, moving coil is mounted here. So, working principle is first considering the current which is fixed in the moving coil, which is represented as IF and IM respectively. The action of the electrodynamic instrument depends upon the force exerted between fixed and moving coil carrying current. The flux density produced by fixed coil is proportional to IF. The force on the conductors of moving coil for a given strength field will proportional to IM and the number of turns N of the moving coil. So, in case of ammeter and voltmeter, fixed and moving coils are connected in series and the developed torque is due to the interaction of the magnetic field produced. So, now moving coil will be proportional to I square, which is IF is equal to IM is equal to I. So, the motor torque is proportional to the product of the current in the moving coil and also the fixed coil. If the current is reversed, the field polarity and the polarity of the moving coil reverses at the same time that the turning force continues in the original direction. Since the reversing current direction does not reverse the turning force, these types of instrument can be used to measure AC or DC current, voltage and power measurement using the wattmeter. Torque equation. First I1 is the instantaneous value of the current in the fixed coil, whereas I2 instantaneous value of current in the moving coil, and L1 and L2 is the self inductance of fixed coil and the moving coil. M is the mutual inductance between the fixed and the moving coil. So, torque equation is derived here. So, here mechanical work is first found out, which is equal to Td into d theta, and assumption for the initial current instrument inductance are given here. So, by deriving this final equation, the torque obtained will be equal to hence Tc will be equal to k theta and theta will be equal to of I square by k into dl by d theta. So, which here shows that deflection will be proportional to the square of the current through the coil and the instrument gives the square law responses. The advantage and the disadvantage is here. The advantage can be used both in DC as well as in AC, and it is robust and simple in construction, possesses high operating torque. It can withstand the overload momentarily. Since the stationary parts and the moving parts of the instruments is simple, it is cheapest. It is suitable for the low frequency and high power circuits, capable of giving an accuracy within the limit of both the precision and industrial purpose. Disadvantages are scale is not uniform, power consumption is higher, the errors are due to the hysteresis and stray magnetic field, change in the frequency causes the error, and the stiffness of the spring decreases as the temperature increases. Error in the electrodynamometer instrument. The main source of the error in the dynamometer type instruments are due to the low torque weight ratio, frequency, eddy currents, external magnetic field and the temperature change. Moving ion instrument. The most common ammeter and voltmeters for the laboratory or the switchboard uses at the power frequency at the moving ion instruments. These instruments can be constructed to measure the current and the voltage to the accuracy needed in most engineering works and still be a cheap as compared to any other type of AC instruments of same accuracy and ruggedness. Working. A plate or vein of soft iron or which has a high permeability steel forms the moving element of the system. It is placed in the situation that it can move in the magnetic field produced by the stationary coil. The coil is excited by the current or voltage under the measurement. When it is excited, it becomes an electromagnet and the iron veins moves in such a way so as to increase the flux of the electromagnet. This is because the vein tries to occupy a position of minimum reluctance. Thus, the force produced is always in such direction so as to increase the inductance of the coil. Classifications. It has both types. One is attraction type and the repulsion type. Attraction type. The coil is flat and has a narrow slot opening. The moving iron is a flat disc or a sector eccentrically mounted. When the current flows through the coil, a magnetic field is produced and the moving arms moves the weaker field outside the coil to the stronger field because of the attraction. So, the control torque produced here is by the spring, but a gravity control can be used for the panel type which is vertically mounted. The damping is provided by the air friction. In the repulsion type, there are two vanes inside the coil, one will be fixed, the other will be movable type. So, it can be of radial type and coaxial type. The picture is shown here. These are similarly magnetized when the current flows through the coil and there is a force of repulsion between the two vanes resulting in the movement of vanes. Comparison between attraction and the repulsion. An attraction type instruments will usually have a lower inductance than the repulsion type instruments, and the voltmeter will therefore be accurate over a wide range of frequency. Repulsion instruments are more suitable for the economical production in manufacture, and nearly uniform scale is more easily obtained. Thank you.